energy. So today we're going to be discussing the energy of electrons and what that means in as far as the way that we identify atoms in certain situations. So we're talking about the energy of electrons and something called emission spectra. So when an electron is in its lowest possible energy, so its natural state, we call it the ground state. It's its energy it has normally. It's without adding any extra energy to the atom. That's the ground state. All right. If energy is added to the atom, then the electrons are going to actually jump to a higher energy level. So in its ground state, the electrons are where they normally are in their normal situation, in their normal configuration that we've been talking about the last couple of days with those S&P orbitals and which energy levels they're in. In its ground state, that's where it is. Now, if I add energy to the atom by heating it up or adding light to it or shining something on it or just whatever, there's multiple ways to do it. But if I add energy to the atom, then those electrons will actually jump to a higher energy level. They move out of their energy level that they're in because I'm giving them extra energy, and the energy levels determine what energy what level they're in. So if you add energy, they jump to a higher energy level, and when they jump to a higher energy level, we say that they're excited, because when someone's excited, yay, they have lots of energy, and they'll go crazy, and they have lots of energy. They're really excited, yay, excitement. And then they get tired and they fall back down. All right, they use up that energy. They don't really use it, but when they add energy to the atom, they get excited. They jump to a higher energy level, and then they will fall back down to their ground state or fall back down to the lower energy levels. Now, sometimes they may jump 2 or 3 energy levels, and then they fall back down step at a time. And they may fall all the way back down all at once. But when they fall back down, that jump to a higher energy level and then a fall back down to its ground state is what we call a quantum leap. So you've probably heard someone talk about the phrase quantum leap multiple times. Most of the time in common vernacular, the word quantum leap is used incorrectly, but it is what it is. Quantum leap is when the electrons jump to a higher energy level and then fall back down. Now, they jump to a higher energy level because you add energy to them. So when they fall back down to their ground state, they have to get rid of that energy because the ground state is its lowest energy. So when they have extra energy, they're excited. When they go back to their ground state, they give off energy. And when that energy is given off, it's usually given off in the form of light. And so since it's given off in the form of light, we're going to talk a little bit about light. Now, most of the stuff about light that you need to know, you will learn in physics when you take your physics course. But in this class, I'm going to just give you a little basics of light as we talk about how that pertains to atomic emission spectra. So what we call light is simply a small section of the electromagnetic spectrum that humans can see. So there's a whole range of the electromagnetic spectrum, and that's all frequencies and wavelengths of electromagnetic waves. All electromagnetic waves of every kind fall on the electromagnetic spectrum. Only the small little bit that the human eye can actually recognize is what we call light. But as you look at this, as you look at the diagram here, you notice that the long wavelengths are things like broadcast band, that's like TV signals, and radio signals and radar and microwave. So your cell phone signal is right around here. Light is in this range right here, and you see the rainbow there. And then you have ultraviolet, X-rays, gamma rays, cosmic radiation as you get to shorter wavelengths. Now you'll notice that to the longer side, you have red, and the shorter side you have violet, and infrared comes before red. That's actually what infra means. So infrared is before red, and ultraviolet is beyond violet. So you've got the infrared, which is how we perceive and recognize that as heat. So the infrared light from the sun is what we get from the heat we get from the sun comes to us through infrared. And then you have red, and it progresses through the rainbow: red, orange, yellow, green, blue, violet. And then after violet is ultraviolet. We can't see ultraviolet, but we can feel the effects of ultraviolet when we get a sunburn. All right. So that is what light is. It's just an electromagnetic wave. And that electromagnetic wave, a very narrow band of frequencies of electromagnetic waves are what we call light. So let's talk about waves for a second. You're going to learn a lot more about waves in physics, but I'm going to define a couple of words for you here. First, we have the wavelength, and it's represented by that funny little letter there that you see. That is the Greek letter lambda. Looks like an upside down Y. And the wavelength is the length of a wave. That's why it's called wavelength. And it's measured from the peak of a wave to the peak of the wave. So if you have a wave, it's from the top of the wave to the top of the next wave. That's the wavelength. All right. Then you have frequency, and frequency is exactly what it sounds like. It's how frequently the wave happens. So it's how many waves pass a given point per second. So how many of those wave tops, if you're standing out in the ocean and you're watching waves come by, it's how often the waves pass you, how often those waves come by. That is the frequency. Frequency is measured in a unit called hertz, Hertz, hertz. Symbolized with an HZ. And actually, if you look at your radio dial and the old dial radios, and you have the radio frequency, like your signal of say 101.6 is the radio looking to, you'll notice over on the side it says either MHZ or KHZ. It's either megahertz or kilohertz. So a kilohertz would be 1,000 hertz, and megahertz would be 1,000,000 hertz. So that's the frequency of your radio signal. Okay. It's measured in hertz. Now, why is this important? Well, wave speed, the velocity of the wave, v, is found by multiplying your frequency and your wavelength. So you take frequency times wavelength, and that gives you the speed. Why does that matter for us? Well, all electromagnetic waves travel at the same speed. They all travel at the speed of light. We call it the speed of light because that's what we see, but light is an electromagnetic wave. All electromagnetic waves travel at the same speed, the speed of light. And that speed is represented by the letter C. And it's 3.0 times 10 to the 8th meters per second. That's 300 million meters per second, or 186,000 miles per second. That's really, really fast. And in fact, if Albert Einstein is correct, then that would mean that nothing travels faster. That is the fastest possible speed in our universe. So that is the speed of light. So it is constant for everything, okay? Speed of light is constant universally everywhere. And so if all waves travel at the same speed, then our speed equation becomes simply C equals lambda F, because all of them have the same speed. Their speed is C, the speed of light, all right? Lambda is the wavelength, and F is the frequency. So if they all have the same speed, if our C then is constant, that's the same for everything, then what that means is our lambda and our frequency are related to each other, okay? So if your speed of all the EM waves is constant, then a higher frequency means a smaller wavelength. So if this number is constant, then if my frequency increases, my wavelength must decrease. It must go down. So let's just use simple numbers like 2 and 3. If wavelength is 2 and frequency is 3, then C would be 6. Our speed would be 6. 2 times 3 is 6. Okay. Now, if it has to stay 6, it has to be constant. That means that if my wavelength goes down to 1, it was 2, and it goes down to 1, that means my frequency that was 3 has to go up to 6, so that 1 times 6 is still 6. It has to stay constant. So if my frequency increases, my wavelength has to decrease. And not just that, if my frequency doubles, then that means my wavelength has to be cut in half. And if my wavelength doubles, then the frequency is cut in half. It is what we call a direct or an indirect relationship. If one goes up, the other goes down by the same amount. They're indirectly proportional. Okay? It's by the same proportion. So if I double one, the other one gets cut in half. If I triple one, the other one gets cut in thirds. So it is an indirect proportionality. That is very important that you understand that. Now, I'm not going to have you in this class make you calculate any of this, but you do need to understand the relationship between frequency and wavelength is an indirect relationship. Okay, so when that comes to the energy, when that electron falls back down to its ground state, it jumps to the higher state, it gets excited. When it falls back down to its ground state, it gives off energy in the form of a quantum of light. Now, a quantum of light is called a photon. A photon is the smallest particle or the smallest portion of light. Now, the frequency of the photon given off during a quantum leap is determined by the energy that is released. Okay, so when it gets excited because you add energy to the atom, then the electrons fall back to their ground state. They're going to give off photons of light. When they give off those photons, the energy they give off is determined, or the frequency of the photon is determined by the energy that is given off. Now, this was something that was first discovered by a man named Max Planck. Now, Planck's equation for the energy of a photon is this: E equals hf. And in this equation, h represents what we call Planck's constant. And Planck's constant is a universal constant for everything. So it's basically just like a multiplier for the frequency. So you have the energy equals Planck's constant times the frequency, which tells us that the energy of a photon is directly proportional to its frequency. So if I have a high energy, I'm going to have a higher frequency. If I have a lower frequency, I'm going to have less energy. So high frequency photons are high energy photons. Low frequency photons are low energy photons. The photon energy and the photon frequency are directly related to each other. If I double the energy, I'm going to double the frequency. It's a direct relationship. All right. Higher frequency means more energy. So if you look back at that electromagnetic spectrum I showed you earlier, you'll notice that violet is actually the shortest wavelength, which means the highest frequency. Red is the longest wavelength and therefore the lowest frequency. And if it has the lowest frequency, it has the lowest energy. So actually red is the lowest energy color of light. And violet has the shortest wavelength and therefore the highest frequency of visible light, and therefore it's also the highest energy, which is why when you are burning things, you want to look at the color of the flame. A red flame is actually a very cold flame as far as flames go, and a blue flame or a violet colored flame is much hotter because it's higher energy. Higher energy means higher frequency. Higher frequency means shorter wavelength. Red has a long wavelength, violet has a short wavelength. And so the rainbow goes in the order of red, orange, yellow, green, blue, violet. And those are also the order of the energy. Red is the lowest energy, violet is the highest energy. All right. Now this helps us understand something we discussed previously. All right, the atomic emission spectra and why Rutherford could not explain with his model of the atom. So when energy is added, the electrons get excited, they fall back to their ground state, and they give off light in the form of electromagnetic waves. Now, atoms have more than one electron. These electrons all jump and fall back down at different rates, different times, different amounts, and so they're all going to give off different frequencies when they do that. So when one atom gets excited and its electrons jump to higher energy levels and then they fall back down and give off light, they're going to give off a lot of different frequencies of light. They're going to give off a lot of different energies and a lot of different frequencies. So you have multiple photons being given off at the same time. Now, when all of that light is given off by the atoms, the element, if you look through something called a spectroscope, it's a device that allows us to take the light we see and split it up into all of its different frequencies. It's basically just like prisms. So you remember, you take a prism, you shine a light through it, and you get the rainbow out of it. If you have white light that has all of the frequencies of light, and it separates it into a continuous rainbow. Well, if you shine light on it that doesn't have all of the frequencies, it's still going to separate them, but it's going to separate the frequencies that are there. And so you're going to have gaps. That's what a emission spectrum is. All right. When we shine the light that comes from a element, as it's given off the light from being excited in ground state, those quantum leaps, as it gives off that light, as we look at that light and we put it through a spectroscope, which basically separates the light frequencies, you get a pattern. That pattern is called an emission spectrum. Now you're looking through it, you're going to see a field of black with a bunch of colored lines on it. So you'll notice here that you've got hydrogen, neon, and beryllium here in this diagram. And so hydrogen, you've got a little red band and a blue band, and it's hard to see here, but you've got a couple other colors. And then neon, you've got other colors given off. Beryllium, you have even more different bands. And so we can actually use that to identify the element, because every element's emission spectrum is different. All right. It's like a fingerprint for the element. In fact, the emission spectrum is how the element for helium was actually discovered. Now, we now know that we can get helium here on Earth. There are sources of helium on Earth, but helium was first discovered from looking at the light from the sun through a spectroscope. All right, because the emission spectrum of helium is what allowed us to separate and identify it differently than the hydrogen in the sun as the light was coming off. And that's actually why it's called helium. It's named after the sun, or in Greek, Helios. So that's why it's called helium, because it was discovered from the emission spectrum of the sun. So it's like a fingerprint. That's how we're able to tell what things out in space are made out of. That's how, when you are watching those documentaries and they're talking about how this distant star is made up of this, this, and this, and the atmosphere of Saturn is made up of this, this, and this. Well, it's because we look at the emission spectrum of the planet. Whenever the light from the sun hits it, it excites it, and it reflects that light back. It becomes illuminated and shines the light back. We look at that light. We look at it through a spectroscope. We can break down and see the different fingerprints of the elements that are there, and that's how we're able to know the composition of things far out in space by using emission spectra. Now, another thing, the opposite of emission spectra is absorption spectra. All right, we can look through a material, so we shine light through a material, and some wavelengths are absorbed. In fact, the same wavelengths that are emitted whenever you excite it, those same wavelengths of light get absorbed whenever you shine it through the material. All right, and that absorption spectra, we see a black bands on a field of color instead of color bands on black. So it's kind of the opposite of emission spectra. So you actually see here, you've got the absorption spectra, the top one, you have the full rainbow with these black bands that are the frequencies that are absorbed by hydrogen. And now just below it, you have the emission spectra. So it's the black bands with the light being emitted by hydrogen. So you'll notice that the emission spectra and the absorption spectra of an element actually line up. So if you were to overlap them, you would get the full rainbow coming through. So that is absorption spectra and emission spectra, and it is all about the energy of the electrons. When those electrons have energy added to them, they jump to their higher energy levels, and then when they fall back to their ground state, they give off light, and its specific frequencies are given off by specific elements. All right. So we're now going to look at a few examples of these emission spectra in a fun, hopefully cool way. All right, this is air through a tube lit up with electricity. It's just shining a good old air. We'll send it through a diffraction grating to get the emission spectrum, and you can see all of the different bands of color all separated out. This is air's emission spectrum. Air. Trippy. This is the noble gas argon and its emission spectrum. And there we go. That's nice. Argon. Alright, so this is helium. You can see how it kind of looks like the sun because, well, that's mostly what the sun is. Hydrogen and helium. So with the diffraction glasses, you can see the diffraction and the emission spectra of helium. You notice that you've got A little bit of red, yellow, there's some blue, and a very little bit of green you can barely see in there, but lots of black bands in there between the colors. There's the emission spectrum of helium. And this is neon, which you're familiar with all those neon lights. And this is the emission spectrum of neon. So you'll notice over there on the right, you've got a little bit of reddish pink and orange and yellow. Not much green or blue anywhere. So that is neon. This is oxygen, good old O2. And here is the emission spectrum of oxygen. Alright, so you see it separates a little bit of bands there. Alright, oxygen. Alright, so this is water vapor lit up in the tube. So with the diffraction, so we see the emission spectrum, and you can see how water splits it out. So you've got lots of breaking apart of the colors. That's water. So now that you've seen all of these emission spectras and you've looked at it, you've gone through it, we're done talking about the energy of the electrons. We talked about the electron configuration. So hopefully you have a better understanding of how electrons fit in the atoms. And when we move on, we're going to see how those electrons will interact with electrons of other atoms as we create bonds and get into the actual chemistry of chemistry. So I hope you had fun. Thanks for watching. Have a day.